This next lesson would have been the first lesson for Unit 3, the conservation laws. It focuses on work and energy and efficiency. Um, so you would have dealt with a little bit of energy last year in Physical Science 20 when we talked about enthalpy and the quantity of heat energy transferred when you're heating or cooling an object. So it will touch on that a little bit. Maybe not this lesson, but eventually. So this lesson is going to focus on a quantity called work. Before we get to that, just a brief reminder that if we're going to deal with the conservation laws, I have to say it out loud that energy cannot be created or destroyed. However, it can be transformed from one form to another. So all the energy that's out there in the universe has always been there in the universe and will always be there in the universe. It may not be consistent in form, but it has always been there and always will be there. So that is one of the major underlying laws of physics that you kind of have to just always keep in the back of your mind. So if you look up energy, most dictionaries and encyclopedias will just give you the definition. It's the ability to do work. And then if you look up work, it'll probably just say work is the amount of energy. So those are cyclical definitions. They don't really provide much of a definition of anything. So I like to think energy is the ability for motion, if you want to think of it in that regard. You have different types of energy. You have kinetic energy, you have potential energy. Kinetic energy is the energy of motion itself, and potential energy is energy that is stored up, just waiting to be converted into kinetic energy. But we'll talk about kinetic energy in a different lesson, and same thing with potential energy. So you think of energy as some kind of ability for motion, whether it's actually moving or just getting ready to move. Then work can be defined as the force that's causing the motion as it moves over a given displacement. If you can think of it like that, then the definition kind of will make sense in some of the slides that we have coming up here in a moment. So there's Joey. Joey's pushing a box. You might have had to do some manual labor jobs where you have to move things, or maybe you just did something around your house where it involved you pushing the table across the floor. A lot of times when you end up pushing a box, if you think of it that, you're not always getting level with the center of mass and pushing horizontally. You'll often be like Joey, where Joey's being a little lazy. He's pushing down at an angle. The box is on the floor, so it can only move to the right on the screen, so it can only move forward. But Joey's force is not moving just forward. It's also going down. There's two components to his actual force that's acting on this box. So in order for this box to move, he needs that applied force, but only one of these applied forces is actually going to contribute to the motion, and that is the parallel acting force to the displacement. This is the force that's going to do work. So work, again, is defined as measure the amount of energy, so therefore this is the only force that is going to contribute to transferring any energy to the box, which contributes to its actual motion. So the other force, this perpendicular force, is not contributing to the motion. So that perpendicular force is not doing any work. So if you look at work mathematically, work is your parallel acting force to the displacement of motion multiplied together. If they are not parallel with each other, that's where trig comes in. So if there's an angle between your force vector and your displacement vector, you would just multiply by cos of the angle between those two vectors. And then you get a more common form to be work is equal to your force times your displacement multiplied by cos of the angle between them. Force, of course, and displacement are vectors, but when you multiply two vectors together, you're doing something called the dot product in calculus. You can Google that if you want. It's not something you need to know how to do, but typically when you do the dot product in calculus, your vectors become scalar values. So you can just take my word on that and move forward from here. Energy is not a vector. You either have energy or you don't, for the most part. You can gain energy, you can lose energy, you can technically have a negative energy in certain scenarios, but we'll get to that another time. So this is the simple equation. If your force is parallel to the displacement, then your angle would just be 0, and you can more or less ignore cos theta because cos of 0 is 1. The units for energy is the joule. Again, you would have seen the joule last year in Physical Science 20. If you break down the equation, it's a force multiplied by displacement. So you have a Newton times a meter, and if you break a Newton down into a kilogram meter per second square, multiplied by a meter, it gives you the fundamental units of a joule to be a kilogram meter square per second square. So as I said on the other screen, if your force is already parallel with the actual displacement or distance, as I have typed there, then your angle between your force vector and your displacement vector is 0, and cos of 0 is 1. So it doesn't actually alter the equation by anything too crazy. In the case that I have here, the example that I have here is just a rocket ship. In order for that rocket ship to actually move upwards, it needs a thrust. So it needs some kind of force to make it go upwards. So the direction of the net force going up and the actual direction of the displacement of the rocket are going in the exact same direction. Therefore, there's no angle between their two vectors. Therefore, theta is 0, and we can have this simple equation. And you'll see this equation will be good enough for a lot of the work problems that you actually do. If there's ever a chance where you have an applied force that's acting on a mass that is not contributing to motion, for instance, you have, let's call this guy George. George is holding the box, and for some reason he's on skis moving forward. So that's a weird scenario, but we're going to go with it. He's holding this box. Now, it probably takes a little bit of effort to hold the box vertically, but since he is moving to the right, this effort force is not contributing to the rightward motion. So because of that, this force right here, holding the box up, is not contributing to any work. The one way you can also look at it is you have a 90-degree angle between the force vector and the displacement vector. And whenever you have a 90-degree angle, you have a perpendicular force, and perpendicular forces do not do any work on a system. So no work is done here in this scenario. So we have a quick little question here. Suppose we have a mass. I don't have the mass drawn on here, but suppose we have a mass that's traveling some displacement of 25 meters at a 25-degree angle, and the force acting on it is just moving horizontal. So this can either be an inclined plane, or it can just be on a track where it's only able to move at this 25-degree angle. You can take your pick, whichever one works better for you mentally. But we have a difference in direction of your force and your displacement vectors. This is not a free body diagram. Normally we don't connect vectors together. This is just a simple diagram to get a point across. So the force acting on is 150 newtons. It travels 25 meters at a 25-degree angle, difference between the two of them. So question asks, what is the work done by this force? So you would just state the two things you know your force vector, you know your displacement vector. So it would just be a matter of multiplying the two together and then accounting for the 25-degree angle difference. So plug in those terms in, 150 newtons multiplied by 25 meters multiplied by cos of an angle of 25 degrees. Make sure your calculator's in degrees, not radians. This entire course you will not be dealing with radians, so always make sure you're in degrees. So if you multiply it through, you should just get 3,400. A Newton times a meter, of course, is a Newton meter, which gets converted into a joule. 3,400 joules is how much work should be involved, which I would call just 3.4 kilojoules, because I like metric prefixes, and I think it makes the questions or the answers look a bit neater to digest. So by saying 3.4 kilojoules of work is done, that is how much energy has been added into this mass that moved 25 meters. So it increases in energy, therefore you have motion. So if we actually had this force acting in the exact same direction as this displacement, then we wouldn't deal with the 25-degree angle difference, so cos 25 wouldn't exist. And then we could just say that we have more work that's being done, you have more energy delivered to the system, you'd have 3.75 kilojoules of energy delivered to the system. But cos 25 is about roughly 91.91 or 91% if you want to think of it that way, of the actual force. It actually reduces the amount of work done. So typically if you're going to do any work, if you're going to actually move something with your own physical strength, you always want to try to make sure your force is acting the exact same direction that you are moving, and you'll require less effort on your end. If you have multiple forces on an object, you can do multiple work if you think of it that way. You can have positive work, you can have negative work. Negative work would just be removing energy from the system. But typically, you will want to find the net parallel force in most situations. So you can do negative work. You'll see that a lot with friction in your practice problems. Friction removes energy from a system. And so for an example of that, I've got a man pulling his little girl, or father pulling his daughter in a little wagon. He's going to pull her to the right, and the wagon will make an angle of 30 degrees. If the man applies a 50 Newton force, an angle of 30 degrees, the wagon's only going to go forward. And it is going to have a little bit of friction involved. So we'll call it just 5 newtons of friction because that's what the picture says. So the work done to move the wagon is the sum of the work done by the man and the work done by friction. So you can separate it into two different work equations. So the work done by the man plus the work done by the friction. So they would have two separate equations. You'd want the parallel acting force provided by the man multiplied by the displacement moved by the wagon, likewise added to the parallel force of friction multiplied by the distance the wagon travels. Friction is always parallel to the direction of motion. It's just always going to be in the exact opposite direction. So if I incorporate the equation, which I didn't write it down for some reason, if I incorporate the equation for each of them, your parallel acting force for the man would be your force multiplied by cos of the angle multiplied by the displacement traveled. So in this case, I got 50 times cos 30 times 30 meters, and that'll give you your parallel acting force. Your friction is, of course, 5 newtons multiplied by cos 180, because the direction of motion, according to this purple vector, is to the right. Friction's acting to the left. That makes a 180-degree angle difference. If you'd rather just get rid of that cos 180 and call this -5, that also would have been fine, because cos 180 is, of course, -1. So -1 times 5 would just be -5. So you end up with an overall value of the man is doing positive work of about 1,300 joules, and friction is doing negative work. It's removing 150 joules of energy. So if you simplify it and just add them together, you should have a total amount of work done on the wagon to be 1,150 joules, or 1.15 kilojoules. So that's one way to look at this problem. You end up with negative work done by friction. And sometimes negative work can just be in a form of, maybe you've got a guy named Bob here doing tug of war, pulling the wagon in the opposite direction. So in that case, that could also be considered negative work, because you'd be doing work against the direction of motion. So it doesn't necessarily have to just be friction. Different way to attack this problem is to use your knowledge from last unit, just forces. So I would consider drawing a free body diagram. There's my free body diagram. I don't have, thought I drew it on there, but I guess not. Weight and the normal force, I guess, are ignored here. But here you have your applied force at that angle theta, 30 degrees. You have your friction going left. Should have my weight going down and my normal force going up. The only force I want to use here is going to be my parallel acting force for my applied force, because that is going to be in the direction of motion. So, oh, there it is. Just wrong order for the slides. Sorry. My normal force is going up, my weight is going down, and then of course I want to use that actual parallel acting force. So when I do my net force, I don't necessarily want to find the mass times the acceleration in this regard, because I don't know what that little girl's mass is, and I don't want to find the acceleration, but my net force is of course the sum of all my forces. So I'm going to deal with the x direction only. So my applied force by the man is going to be the hypotenuse multiplied by cos of my angle, so 30 degrees. I'm going to want to add my force of friction. So that ends up just being 50 times cos 30, and then add my friction, which is going left, so we can just call it -5. And that makes it somewhat more palatable without having to plug in that cos of 180 for the friction. You can just write it out this way if you want. Now that gives you an overall net force of approximately 38.3 newtons. That's just a rounded figure, of course. If you work it into the work equation, our net force is now parallel. I don't have to worry about multiplying again by some cos of an angle. So this net force is in the x direction only. This wagon's only traveling in the x direction. So I can just take my answer there, my 38.3 newtons, multiplied by the displacement of 30 meters, and that'll give me the exact same result as the other way of doing it. Whichever way you decide you want to do this problem is up to you. Both cases are 100% correct. It's just two different ways of doing the exact same thing. So again, this is just back on here to kind of remind you that this is an example where negative work is done. Other things that you're going to see in your work problems are times where work is talking about how energy has transformed. So in that last case, the man was pulling the wagon. He was contributing to the wagon's motion. And so he was adding energy to that motion. So it is an actual change in energy. And that's really all work is, the energy transformation, which means a change in energy. So sometimes you'll want to just see it written down as a final energy minus initial energy if you're actually aware of what those energies were before and after. So that's one way you can calculate work. I think there's a couple examples in your work problems where you will have this situation. There will be other times where you just want to know the force and the displacement involved. But then there's times you can relate this back to kinematics and find everything using mainly kinematic information along with mass. So one way to look at that is to recognize that if work is your parallel acting force multiplied by your displacement. I don't have vector symbols drawn, but they were vectors. So if we just assume there's only one simple force acting on it, or that we have the net force, we won't worry about the situations, but there's lots of other forces. If we just have one simple net force acting on a mass and it travels the displacement, we can break that down into your net force is your mass times your acceleration. And displacement, there's a couple of different equations we could use for displacement. I'm going to use equation 5 from kinematics because I find this one the easiest one to manipulate without it being too challenging. So if I want to solve for my displacement, I'll need to bring my initial velocity squared to the left. I'll have to divide both sides by my 2 times my acceleration, and that'll give me an equation for displacement, which I can then substitute into my work equation. So once you put your displacement in with your work equation, you can see that the accelerations should just cancel out. And then you can rewrite it as a relationship between mass and how your velocities have changed. But of course, this is a squared velocity, so don't find your change in velocity then square it. Take your final velocity square minus your initial velocity square. If there's been no change in your overall velocities, then no work is done, right? No energy has changed in the system as far as we're concerned. So that's another thing to kind of notice with work. It will often change the speed or the velocity of an object when you are applying this force. So that's just something else you can use for some of your problems to calculate work. So the last little bit, almost the last little bit of this lesson will be about efficiency. So we're going to use the Greek letter eta, is how it's pronounced, ETA, eta. It's a fancy looking N. So N with an extra little bit of a tail if you want to think of it that way. It's the amount of work obtained from a machine. Losing my speech. The amount of work obtained from a machine is always less than the amount of work put into it. This is because some of the work is lost due to friction. Think of your car engine. As your car runs, your engine will get hot. Not all of that combustion is being converted into the motion of the piston. It gets absorbed into the engine itself. The engine gets hot. All that explosion in the combustion, a lot of that gets converted into exhaust, and that exhaust is hot as well. So as that comes out of your vehicle, it heats up the muffler, and that transfers a lot of that usable chemical potential energy into just wasted energy. And it's just wasted in the form of radiation, or in some cases in the form of friction. Not all of that energy can get converted to work, and not all the work that you do on a system is going to get contributed to motion. So sometimes things just get lost. So that also plays into the second law of thermodynamics, the simple version, where the flow of energy is always from the hot to the cold. So energy is going to get lost no matter what. There's no such thing as the perfect, efficient machine. So efficiency of machine, motor, or system can be calculated using the following formula. So for that, we just take our efficiency to be the work or energy output divided by the work or energy input multiplied by 100%. So our efficiency is a percentage. When you put it in the form of equation, it looks like that. Your work output divided by your work input multiplied by 100. In the form of a question, suppose you have a motor that uses 1,350 joules of energy just to raise a 30 kilogram mass 2.4 meters into the air. How much work was done to raise the mass during the lift, and calculate the efficiency of this motor. So since we're going to raise something up in the air, we're going to use weight, because that would be the very minimal amount of force needed to apply just to make something move. You basically have to match its weight. If you want it to go up faster, you have to have a force greater than its weight. But if you're just looking at the bare bones minimum, a force needed to go up just has to match an object's weight. And we weren't given more information, so we'll just assume the bare minimum. So from that, to calculate the work, we'll just take the weight multiplied by the displacement. And so we're going to assume we're talking about the applied force going up, the displacement going up. Didn't draw the vector symbols. So your weight, of course, would be your mass times your acceleration of gravity multiplied by your displacement going upwards. Plug in the numbers, right? 30 times 9.81 times 2.4, and you'll probably get something really close to 700. So 706, if you punch it through your calculator, that would be the joules. That would be the minimum amount of work needed to actually make something go up in the atmosphere. That's 30 kilograms, and you want to raise it 2.4 meters. Now, this motor for the crane or whatever it is that we're using to raise it took almost twice that amount of energy, right? In order to make something go up, it took 1,350 joules of energy just to make this thing go up in the atmosphere. So if we look at that and talk about the efficiency, so that's your work output divided by your work input. So your output would be, this is the energy that's needed, right? That's your 706 joules. The energy that you used, the input energy, that is your 1,350 joules. So if you do that ratio, 700 divided by 1,350, joules will cancel out, and you'll see that you'll get about 52% approximately. So this machine, this motor, is only 52% efficient.